Well, thank you. So it maybe looks to you as if I've dropped the unconditional from the title, but it is really unconditional secure quantum signatures. So the people who are involved in this work are mostly from Heriot-Watt University. That's in Edinburgh, Scotland. But we also have here, back. So Juan Miguel has been doing a PhD with Norbert Lütgenhaus in Waterloo, and John Jeffers is at Strathclyde University. Vedran is now in Innsbruck, but mostly Edinburgh. So what's a signature? And I should say I'm really, really happy to take questions during the talk. If something is unclear, just wave your hand or shout. So a signature is something which is really widely used. So when you send email, for example, you're very likely to use signatures, or in electronic commerce. It's something that's different from encryption. So the message is not secret, but it's tamper-proof. So Alice, a sender, can send a signed message so that a recipient, so here Bob, can be sure that the message did come from Alice and that it wasn't tampered with. And in addition, and this is what distinguishes a signature from authentication, Bob can forward the message to some other recipient, Charlie. So when he receives the message, he can already then check that if he would forward it to Charlie, Charlie would also accept. So this would be akin to, say, if Alice writes a check and signs it and gives it to Bob, Bob is sure when he receives the check already, without then asking Charlie at that point, that when he takes it to Charlie, who owns the bank, Charlie will also accept the check. So that's the signature functionality. So in other words, the message is transferable. So Bob can know that if he forwards the message to Charlie, then Charlie will also accept it as coming generally from Alice and not having tampered with. So what could go wrong here? So one thing is that Bob or Charlie could try to cheat and try to send a message that the other one accepts as coming from Alice. So that would be forging. And another thing that can go wrong is Alice can try to cheat by sending a message that gets accepted by one of the recipients, but then when it's forwarded, doesn't get accepted by the other one. So that would be, the message isn't transferable, which in general will be linked to repudiation. So Alice, if she tries to deny having sent a message that she really did send, she would be trying to repudiate the message. So these are the two things that can go wrong, and so we want protection against forging, no forging, and against repudiation by Alice, or we want transferability. And it's important to note that a difference to QKD would be, in QKD, you're assuming Alice and Bob to be honest, whereas here, any of these three participants, or more generally, any of the participants you can have more than three participants, any of them can be dishonest. So that's the difference. And in this case, it doesn't make sense when you have three parties. If two of them are dishonest, then they can always trivially cheat on the third one. So if you have three parties, you assume that at most one is dishonest. And in general, if you're deciding disputes by majority vote, then you would need half of the participants to be honest. You don't have to know which ones, but half of them should be honest in that case. So that's some basic properties. So, next. Yes. So classical schemes, i.e. non-quantum schemes, to do this functionality, they work using public key cryptography, essentially. So you might think of if Bob is able to decrypt a message using Alice's private key, then he can be pretty sure it came from Alice. Now, public key schemes, they're a little more complicated than that, but that's the kind of basic idea. So such a scheme would use what's called a one-way or trapdoor function, where f(x) is something, I keep pressing next when I want the pointer. So it's easy to calculate one way, but hard the other way. And now the issue here is that we haven't proven that this holds for any function. So we think it holds, but it's not proven to hold. So if you would like to have some more secure schemes than that, something which has a so-called information theoretic or unconditional security, then you can construct such schemes, also without using any quantum features. So the schemes that seem to be around before I started working on this, and my coworkers, there was a scheme by Chaum and Royackers, which essentially is based on the Dining cryptographers, if there are computer scientists in the audience. And it needs secret channels plus an authenticated broadcast channel to work. And an authenticated broadcast channel is not easy to implement. That's a tricky thing. There is another scheme by Hanaoka and co-workers, which needs a trusted initializer to set everything up, in addition to secret communication channels. And there is a useful paper by Swanson and Stinson that reviews these things and points out some issues. Essentially, it's not even trivial to define the functionality of what you mean by an unconditionally secure multi-party signature scheme, and et cetera. But this is, we should be aware that such schemes exist. So if we want to try and do without these problematic assumptions of an authenticated broadcast channel or a trusted initializer, then we can do so if we use quantum features. So the first proposal for a quantum signature scheme was by Gottesman and Chuang. That was already 14 years ago. And this is something that very much resembled a public key signature scheme. And this initial scheme, so this would be the executive summary of my talk. So this initial, very much like public key schemes, quantum signature schemes, have evolved now into something that more and more resembles QKD. So that's the story. And you have to be a bit careful because, as I said at the beginning, in QKD you assume that Alice and Bob are honest. And in a signature scenario, they might not be honest. So when you do your security proofs, I will not talk really at all about the technical details of security proofs, but this is just to mention what you have to be careful with. You cannot just take your security proof for QKD and it's all automatically valid if you use some similar setup in a signature scheme. You have to allow for the fact that Alice could be dishonest, Bob could be dishonest, Charlie could be dishonest. You have more parties than two also. You don't have just Alice and Bob. And you have to be a bit careful also with what the security proof implies. So it has to guarantee the signature rather than, say, information held by an eavesdropper. But basically you can use QKD, certainly QKD experimental components is what you can use. Okay. So, so let's look at how one of these schemes would work. Now there's many variants. As I said, it's evolved all the way from schemes resembling public key schemes to schemes which more and more start to resemble QKD. But the basic principle, and this is also similar to the original scheme by Gottesman and Chuang. So if you pick some set of non-orthogonal states, non-orthogonal quantum states, in the simplest case, two states A and B, and Alice picks some sequences of these states and she sends them to Bob and Charlie. In this example here, she's picked the same sequence to send to Bob and to Charlie. But she could also pick different sequences. There's variations on these schemes. And then Bob and Charlie make some measurements. In this case, I've indicated that they make something called an unambiguous quantum measurement, but they could make some other kind of quantum measurement as well. So this unambiguous measurement is sometimes, when it succeeds, it will give them perfect information about whether the state was A or B. that's in the ideal case, it's 100% correct. And then sometimes the measurement will fail and give them no information whatsoever. But they could also do some other type of measurement, and in general, they would obtain partial information about what Alice has sent, because it's not possible to distinguish completely what Alice has sent. So Alice has full information about what she's prepared, and Bob and Charlie have partial information. And then, roughly speaking, to sign a message, which could be a lot later on, Alice just gives the message together with the corresponding sequence that she's prepared, and Bob and Charlie check whether that agrees with what they measured. Now I skipped some details here, so let's look at the details. There is this distribution stage, and all the quantum action is contained in this stage. So that's at least in the schemes that we've been working on lately. The original scheme by Gottesman and Chuang assumed quantum memory, which obviously was a big difficulty. But it turns out you don't need quantum memory. So Bob and Charlie can immediately measure these states when they receive them. Okay, so how can Alice sign different messages? She doesn't want to have to pick the message, say, 1 month in advance of sending it. So when you set the scheme up, you allow for the message either later being 0 or 1. This is the simplest case with a 1-bit message. To sign longer messages, you can, for example, suitably iterate the protocol. You have to have some way of securely marking where a message starts, ends, and so on. But this can be worked out in principle. So this would be just a simple case of a 1-bit message. So you have some sequence of states that belongs to 0, and some other sequence that belongs to 1. And she sent these to Bob and Charlie, and only Alice knows exactly what they are. So these are some examples of protocols that work roughly like this. Most of them are saying that Alice should be sending the same state to Bob and Charlie. This last one, there's also a poster at the conference, number 37, talking about this last one here. And this is nice in that it does away with an assumption that these earlier protocols all had, in that the quantum channels between the participants should be tamper-proof, in a sense, with the understanding that you can do some sort of procedure similar to parameter estimation in QKD to guarantee that. So this paper by Yin et al., in addition with a poster by our group and another paper, I'll give the reference later on, they do away with that assumption. So the poster that, I think it's Ryan's poster number 53, and then 37 for this one, if you're interested in the details of that. Okay, so Alice has picked these sequences, and then she's committed, well, she's picked these sequences earlier on, and then later on, which could be much later on, there is an entirely non-quantum, entirely classical messaging state where Alice presents the message together with the corresponding classical information describing those states, and Bob and Charlie checks how well that matches their earlier measurement records. So that's the basic idea. And note, I haven't yet talked about how you guarantee that Alice is not cheating, but that's coming. So, in a way, you can think of quantum mechanics providing a one-wave function. So the public key, the classical or non-quantum public key signature schemes, they work using one-wave functions. And you can think of quantum mechanics giving you a one-wave function in the sense that if you know how to prepare a state, it's easy to do it. Well, an experimentalist might not agree, but it's at least possible in principle to prepare quantum states according to some prescription. Whereas if you are sent a quantum state, just say a single copy of a single photon in a BB84 state, for example, you can't even in principle find out which one it was. So for the BB84 states, you can't learn which one it was. And this is guaranteed by, of course, the Holeva bound. So the information about which state was prepared is limited by the Holeva bound in general. And this works, of course, not just for BB84 states. You can pick any set of non-orthogonal states, such as phase-encoding coherent states, where you have some number of coherent states, say, for example, with the same amplitude. But any collection of non-orthogonal states really will do. So, and as I said, it's not necessary that when Bob and Charlie, or any number of recipients, depending on your protocol, they don't have to measure, they don't have to store the states in quantum memory, which the earliest signature protocols assumed, that Bob and Charlie store these states, and then later on when Alice tells them what state it's supposed to be, then they measure it. They can just as well measure directly when they receive the quantum states, and this is really a key to making the schemes practical. So, for example, suppose we're using the BB84 states, and suppose Bob and Charlie are using the standard measurement they would use when in QKD. They just pick a measurement basis. They measure either in the horizontal vertical or in the plus-minus basis. And what they're going to get then is they're going to rule out one of the 4 states without any basis of cancellation or anything like that. They've ruled out one of the 4 states that Alice could have sent. So to send a signed message, if somebody wants to forge a message, they'd have to avoid picking states that have been ruled out. So if you've just ruled out one state, of course there are three out of the 4 that are safe to pick. And if Bob and Charlie would have waited until a forger or Alice tells them what states they're supposed to have, then that would have been only 1 out of 4 would have been safe to pick. But 3 out of 4 to the power n is still going to go to 0 exponentially, so it doesn't really matter. So either way, the probability to forge ends up being an exponential function of the length of the signature state sequence you're picking. So by increasing the length of the sequence, you can get the security level to be as high as you like. And such quantum state elimination, such measurements, now you don't have to use this type of measurement, but it's particularly simple to analyze. It works also for example, for coherent states, not just for polarization states. So if you have, suppose you have 2 coherent states and they're incident on a beam splitter, and you know from quantum optics that this is what you're going to get out, alpha plus beta over root 2 or alpha minus beta over root 2. And then you know that if you see any light in this output mode 2, then whatever these states were, they can't have been the same coherent state. So of course they don't have to be coherent states, but suppose in the experiment that you're controlling this reference state alpha, and then Alice is sending some other state, which might be a coherent state or might not. But no matter what that state is, even if it's some other fancy entangled state or something, you can be sure that it's not going to be that coherent state alpha if you see any light here. And similarly, if you see light here, alpha can't have been minus beta. So you can eliminate the state you are comparing with in a sense. And you can generalize this to more than 2 coherent states as well. For example, you could have your unknown state in here, and you can split it in half, and here you have a known reference state, which is here alpha over root 2, and here is I alpha over root 2. And clicks in these 4 detectors then will rule out one of these 4 possible coherent states in this setup. So this is what has been used in the Heriot-Watt experiment, this type of quantum state elimination for weak coherent states. And if you know about quantum measurements, then quantum unambiguous discrimination would correspond to conclusively settling on one of these 4 states. So that would be the case if we manage to see 3 clicks here. So then that, if alpha is weak, you have weak coherent states, that happens very, very seldom. So it's very seldom that you're lucky enough to be able to rule out 3 out of the 4 states, and then, of course, it has to be the remaining one. But for signatures, we're happy even if we just manage to rule out 1. That's still useful information. And that's key in getting the experiment to work at least a little better. Right. So I still have to explain how you can be sure that Alice doesn't cheat. And this can be done in the earliest version, in the Gottesman-Chuang protocol. Bob and Charlie, the recipients, had to do some quantum swap test on their signature copies. And now that's quite complicated to do experimentally. So a slight improvement was to use an optical multiport, which we had in earlier experiments. But even it's very, very tricky to realize. So, and it's simple to see. Actually, it's also to see that you don't need quantum memory. I'm surprised that it took so many years for people to realize. And likewise, that you don't have to do a swap test or anything like that. You can just have Bob and Charlie measure. If they measure already when they receive the states, and then secret from Alice, they forward part of their measurement records. So now Alice doesn't know anymore. Maybe she tried to send them different states or some fancy entangled states or whatever. But if they do this exchange, they will end up symmetrizing their measurement records. So it's as if, say, Alice would be given them jars of black and white marbles, and say a jar with 100 marbles to Bob, and another jar with 100 marbles to Charlie, and she might give them different fractions of black and white marbles. But if they take at random half of their marbles and give that to the other guy, and then get back half of the other guy's marbles, then they'll have the same distribution of black and white, no matter what Alice gave them. So this exchange will protect against Alice cheating. And it's also important then that the threshold, the error threshold that holds for receiving a message directly from Alice is stricter than the one you use to check a forwarded message, because Charlie and Bob have the same average fraction of errors or mismatches, and you want it to be unlikely that Bob accepts while Charlie rejects, and that you can achieve by putting a gap between the threshold at which Bob will be happy and Charlie will be happy. So if there's a gap here in between, it's unlikely that Bob sees some fraction down here, while Charlie sees a much, much higher fraction of errors. Yes? Measurements. Well, they could also forward the quantum states. It doesn't matter, but they can just as well forward the measurement results. But it has to be done secret from Alice, and she can't know which ones get forwarded. Yes, but just as well the measurement results. Makes it easier, right? So, if you've seen this, then it's not so hard to realize that, well, actually, this would also work if, say, Alice shares some string of secret bits with Bob and some other different secret string of bits with Charlie, and then Bob and Charlie tell each other secret from Alice half of the bits they share with Alice. And now to sign a message, Alice just simply has to give all the bits. She doesn't know who knows what. So this now would be an entirely classical scheme that works just with secret channels. So you have to have secret channels pairwise between everybody, but then it works. So there is a setup phase where you set up all these secret keys, and then as much time as you like can pass until you then send the message. So then you might wonder, okay, so this can then be done obviously using QKD to exchange those secret strings But of course, you could exchange those keys any way you like. But in particular, using QKD, since this is a conference on quantum cryptography. So you might wonder then, why don't we just do usual QKD plus classical, or this non-quantum signature scheme? Since now we have a signature scheme that doesn't need this authenticated broadcast channel or the trusted initializer. But as we've shown, so I mean, yes, so this is much work in progress, and it's a good question. Why don't you do just the usual QKD? Well, there is a difference in efficiency, and now this is poster number 53, I think. Yes. So what Ryan showed is that the quantum bit error threshold is different in practice. If you first want to distill a key, your quantum channel has to be better. If you go directly for the signature without first distilling the key, it's not as tight, the threshold. So there's a small difference there. So essentially, you could think of doing QKD, you do the parameter estimation, but you stop before you do error correction and privacy amplification, because it's not crucial that you arrive finally at a string of bits which is really secure. Each individual bit is really secret and really perfect. You're just looking for meeting some error threshold. And also, you can show that another thing that might be better in the schemes that don't go via QKD is that in principle, the number of quantum channels could be lower if you do direct quantum schemes. So you might not need channels between every recipient, only quantum channels between the sender and each recipient. But this requires you to have very high quality quantum channels. So again, this is not, well, at the moment we don't have really a very practical advantage for this. But it's an open question and an interesting question, what the best quantum signature schemes are. But we know at least that you can do them just by running QKD in the usual way. So this could be a very nice application for QKD systems, that you're also able to provide the functionality of a transferable message. So I'm almost finished. I just want to mention that you can derive some necessary properties that unconditionally secure signature schemes must have in general, whether they're quantum or non-quantum, no matter what. And for some details of this, you can look at a paper by Juan Miguel, a poster by Juan Miguel and a paper by us in the archive. So that's poster number 55, I think. Yes, 55. They're still up until tomorrow. So these schemes, they can't be completely deterministic, because if they were, then you could forge messages. So that's one property that's absolutely necessary. If there's no limit on what computations any users can do, you want unconditional security, information theoretic security, then different recipients must have different verification algorithms. Because if some of them have the same and they know it, then they can forge a message. So this thing that you have a setup phase, and you have some people who are part of the whole setup phase, and others who are not in the scheme, that's necessary. And you can't have this nice universal verifiability that the public key signature scheme has. And in fact, you might think, or you might say that, well, we shouldn't call these schemes unconditional secure signature schemes, we should call them transferable MACs instead. If there are computer scientists in the audience, it might be helpful to think of them like that. But we're simply following existing terminology. So I'm almost finished. You also need to think carefully about how you resolve disputes and your trust assumptions. For example, if you use a majority vote to resolve disputes, then you need at least half of the participants to be honest. Finally, some open questions that I think are interesting. we know that you can do a signature scheme either if you can do untraceable sending. So participants can send Alice, the sender, bits in the setup phase so that she doesn't know who sent what. That you can use to set up a signature scheme. Or you can set up a signature scheme if you have some type of oblivious transfer so that Alice can send participant information in such a way that she doesn't know who receives what. Either of them will give you a signature scheme. So it would be interesting to have some more a framework for which computational primitives leads to what. And that's the end of my talk. So that's some Dilbert cartoon on signatures where, yes, well, thank you.
Thank you very much. And now the session is open to discussion. So any questions or comments, please?
Thanks, nice talk. There's one point I want to emphasize, because I think it's important not to get this misunderstanding. Here I am, by the way.
Yes, great, yes.
You explained quantum signatures and similarly unconditionally secure signatures as having the same or achieving the same functionality as computationally secure signatures, which makes it sound that we could, in principle, replace computationally secure signatures by quantum signatures. Now, I think there's an important difference, and that is that computationally secure signatures work in ad hoc settings, where we don't know in advance to whom we're going to send a signature, who's going to verify these signatures. Whereas in quantum signature schemes, we need to know in advance, during key setup, who are going to be the people who will be involved in communicating and verifying signatures.
Yes.
And if you think about it, in many cases where digital signatures are used nowadays, we don't know in advance to whom we're going to send signature, who's going to verify signatures.
Yes. So
when you set up your browser, for instance, I mean, you don't know which websites you're going to visit in the future.
Yeah, I think I said that. So I mean, the case where you want to use the unconditional secure signatures, I mean, this will be cases where you have a limited network of participants that you want to send messages to. And I think I also, so as I explained, if you want unconditional security in your signature, then you cannot have this public verifiability. So it's a one or the other. There's no way to retain the public verifiability and still have the IT security. Another thing, I've talked to computer scientists, so another reason to use something like a transferable MAC, if you wish, is if I understand the computational effort required for a transferable MAC can be much lower than that for a public signature. So in the case where you have a finite network of participants, even if they don't want very high security, maybe it's easier for them to use this type of scheme. That's at least what I've been told by computer scientists.
The next question.
Thank you, very nice talk. Could we get the cartoon back?
The cartoon back, yes. Okay.
I didn't finish reading the last thing.
Okay, sorry.
Okay, thank you. And
I've got another cartoon as well.
Okay, so the real question is, so in this scheme, do all participants have to be authenticated to each other? And at what stage does it have to happen?
Okay, I should have mentioned.
And is the authentication outside of the scope of the scheme?
Yes, so you have, I mean, you have some assumptions, just like in QKD, all the classical communication between partners should be pairwise authenticated. And this is something you can do with IT security with Webman and Carter. So is that your question? Yes, because if you don't do that, then you start having man-in-the-middle attacks and so on and so forth. So the classical communication should be authenticated using standard techniques.
But the quantum doesn't have to be.
The quantum channels, you can do something which is akin to parameter estimation in QKD to make sure that they are not tampered with or eavesdropped on. You just have to be sure that your security proof works also when the sending and receiving party are dishonest.
Right, so I think the time is up, so let's thank the speaker again.